What's going on, everybody? Got another video here for you. It's Laplace transforms for an applied calculus class. This has got quite a bit of stuff in it. We're gonna work with Laplace transforms. In a differential equations class, this will probably be split up into several sections. We've got definition Laplace. We're going to use it finding the integral. We're going to use it looking up tables. We're going to learn how to write stuff out like the first derivative and the second derivative of a Laplace transform to help us solve differential equations. And we're going to do inverse Laplace transform. So it's a lot, but the video shouldn't be too bad. All right, so it says the Laplace transform of a function f of t is defined as the function f of s by the equation. So we've got f of s equals the integral 0 to infinity e to the negative st times f of t dt. All right, so I'm going to do just one example of this using the definition. You probably won't use this very much, but I'm going to work one example to show you this. So it says find the Laplace transform of the function f of t equals t, and t is positive. All right. So the Laplace transform of this, let me change colors. All right, so the Laplace transform of t, that's our function, t, is equal to the integral 0 to infinity of e to the negative st, and that's this part, times our function f of t, which is t, times t dt. All right, so we have to integrate this thing. So to do that, well, we're going to have to do what? We're going to have to use integration by parts. So we're going to let u equal t, dv is e to the negative st dt. So du is equal to dt, and v is equal to negative 1 over s e to the negative st. Okay, you should know how to do that by now. Okay, integrating this thing. You can use u substitution if you need to do more work. I'm not going to show it. All right, so when we integrate this, this is going to give us negative 1 over s times t e to the negative st. Okay, remember it's this times this, it's u times v, and that's going from 0 to infinity minus, okay, so now we got minus, and this negative 1 over s, we're going to pull it outside the integral, so the negative and the negative make a positive, 1 over s, 0 to infinity, e to the negative st dt. All right, and so when we got to integrate this now, so that's negative 1 over s t e to the negative st from 0 to infinity, and then that's going to be minus, right? Because when we integrate this, let's just write it all out. So we got the 1 over s here, so that's going to be times negative 1 over s e to the negative st from 0 to infinity. Let's put our equal signs there. So that's equal to negative 1 over s t e to the negative st from 0 to infinity. Whoop, I'm sorry, that should be a plus right here. So that's going to be minus 1 over s squared e to the negative st from 0 to infinity. All right. All right. So now we've got to take the limit of all this stuff as t goes to infinity. That's this infinity part right here. Okay. All right, so let's just look at this part right here. Okay, let's look at this. So as t goes to infinity, let's just come over here to the side. The limit as t goes to infinity of t e to the negative st. All right, so we need to get this in the form limit as t goes to infinity of t over e to the negative, I'm sorry, not negative, but positive st, because when we move it down to the denominator, it changes the sign of the exponent. So you can see here we've got infinity over infinity, which that allows us to use L'Hopital's rule, the limit as t goes to infinity of 1 over s e to the st. All right, and then as t goes to infinity, well, what happens? This denominator gets really big, so this goes to 0. So that's going to be 0, and then when we plug the 0 in, this is going to be 0, because see, we plug the 0 in for t. You see that? So that's going to be minus 0. So this whole term here goes to 0. All right. Now let's look at this one. So when we take the limit, now remember the 1 over s squared, that's a constant. Okay, so we've got minus. Now let's look at this. So whenever we do the limit of this e to the negative st, as t goes to infinity, this term's going to go to 0. See, look at this. The limit as t goes to infinity of e to the negative st. So that's the limit as t goes to infinity of 1 over e to the st. And see, the denominator's just getting really big, and so that's just 0. Okay, so that's going to be 0. Okay. So probably I'm not going to put that minus. If we do, we would have to make that a plus. So let's erase that minus. But we got 0 here, and then that's going to be minus, and that's going to be negative 1 over s squared e to the negative s times 0. And this term right here is 1, so we have 1 times negative 1 over s squared, and the negative make a positive, so we get 1 over s squared. And that's the Laplace transform. Okay? Now, you know, that's using the integral to find the Laplace transform, but we're not going to really do that. Okay? We've got a table that we're going to use to find these Laplace transforms, and it's going to make it easier. Okay, so let's look at the next thing. They want us to find the Laplace transform of e to the 3t. Okay. All right. So if we were finding the Laplace transform of this thing using the definition, that would be 0 to infinity e to the negative st times e to the 3t dt. And we would have to integrate that thing, which that one, it's not that bad, but I mean, we don't want to do that. So what we have here is we have a table, and what we need to do is match this up with something on the table. So let me bring the table over here, and I'm gonna pull this table's gonna come down with us the whole time as we work. But look at this. Okay. All right. So if you see this, we've got e to the 3t, which when you look through this table here, you can see that it looks like this one right here. The difference is this one has a negative. See, it's got negative AT, but we've got positive. So what we need to do is we need to rewrite this one so that it looks like the one in the table. So we've got the Laplace transform of e to the 3t is equal to the Laplace transform of e to the, okay, we're going to write this as negative, as negative 3t, okay? So what I needed to do here is I needed to get that negative sign in there, which is this one right here, okay? And since we have a positive 3, the negative and negative make a positive. And so now in this problem, you can see that a is negative 3. See, a is the number in front of t, okay? So now I have this is equal to 1 over s plus, see, I've got 1 over s plus a. And what is a? A is negative 3. And so this is going to give me 1 over s minus 3. And there's your Laplace transform. So you can see sometimes you're going to have to rewrite some of these things to match what we have in the table. Okay? But, you know, it's a lot easier than integrating. All right, let's look at the next one. All right, so for this one, we've got f of t equals 5t cubed e to the negative 2t. All right, so here we've got Laplace transform. Okay, so before I write this, let's do this. The Laplace transform of, now we got 5t cubed e to the negative 2t. Now, if you notice in the table, the ones that you're looking to match, you see here how we've got this 5. Notice we don't really have any constants in front, okay? So what I can do with this 5 is I can actually pull this 5 out. You can pull a constant out, and that's going to be t cubed e to the negative 2t. All right. Now, let's look and see which one this matches. Okay. So if we look through the table, do you see that it looks like this one? See, we've got t to a power and e to the negative at. Okay. All right. So we've got n minus 1 factorial. And in this problem, what is n? Okay. Now notice we have t cubed, but that exponent is n minus 1. So that 3, we would need to write the 3 as 4 minus 1 to match that, to match the exponent. See, so it looks like the n minus 1. So now we know that n is 4 in this case. Okay, n is 4. And a, well, look at that, negative at, negative 2t. So we can see that a is 2. And so we just plug this in, and that's going to be 5 times, and that's going to be 4 minus 1 factorial over, see, n is 4, so I'm just plugging the 4 in here. That's going to be s plus a, and in this case, a is 2, and that is raised to the n power, so that's raised to the 4th. And so this is 5 times 3 factorial over s plus 2 to the 4th, which this is 5 times, now we know what, do we remember what factorial is? So just to show you real quick, 5 factorial would be 5 times 4 times 3 times 2 times 1. 3 factorial will be 3 times 2 times 1, and so on. That's what the factorial is. So we've got 3 factorial is 6, and that's over s plus 2 to the 4th, and so that would be 30 over s plus 2 to the 4th, and this would be your answer. Okay, let me erase this. All right. So it's not too bad. Not too bad. All right, so let's move on down to the next one. All right, so here we've got f of t is cosine 2t minus sine 2t. And so we need the Laplace transform of cosine 2t minus sine 2t, which that is equal to the Laplace transform of cosine 2t minus the Laplace transform of sine 2t. If you're adding or subtracting functions together and you're looking for the Laplace transform, you can split the terms up and just find the Laplace transform of each one. Now, let's see, this one's easy here, because if you look, here it is right here. There's cosine and there's sine. All right. So we've got the Laplace transform of cosine 2t. A is 2. So that's going to go here. So that's going to be s over s squared plus 2 squared minus, and then for sine, it's A is 2. So we're doing this one now. So that's 2 over s squared plus 2 squared. And so this is just going to be s minus 2. We got a common denominator, so I'm going to combine like terms. And that's just going to be over s squared plus 2 squared is 4. And so there's your Laplace transform. Okay. All right. Let's look at this one. I think this is the last one where we're finding the Laplace transform using the table. All right, so we've got the Laplace transform of 3 plus 2t cosine 3t. All right, so I'm going to split this one up. So that's going to be the Laplace transform. Now look at this. We're going to have the Laplace transform of just a constant term of 3. Okay, but nowhere on here does it say 3. But we do have a 1. So we can take the 3 and pull it out, and that makes that the Laplace transform of 1. See, 3 times 1 would give us the 3. Plus, and then what we're going to do is pull the 2 out, Laplace transform of t cosine 3t. Okay. All right, so this is just equal to what? That's going to be 3 over, well, let's just write it all out. That's going to be 3 times 1 over s. Laplace transform of 1 is 1 over s. Okay. Now, let's see if we can find, that's going to be plus 2, and that's t cosine 3t. Oh, look at there. Look at this. T cosine 3t. So in this case, A is 3, and that's the only thing we have to plug in. See, everything matches. T, cosine, 3t, or AT, and A is 3. So that's going to be times s squared minus, I was fixing to put an A, minus 3 squared over s squared plus 3 squared squared. Okay, and so we get 3 over s plus, and then that's going to be 2 times s squared minus 9 over s squared plus 9 squared. And there's your answer. All right. So you can see it's not that bad. Okay. All right, let's move on down. So that's finding Laplace transforms using a table, and we're going to come back to the table because we're going to do in a minute we're going to do inverse Laplace transforms, and basically what that is on the table. See, when we were finding Laplace transforms, we were looking at this column and going over here, but for inverse we're going to have to find this and go the other way. We're just going to be going in the opposite direction. Whoop. All right. So let's see what we have here. Linearity property. If a times f of t plus b times g of t, well, we got the Laplace transform of that. And let's see, that should be an equal sign there. And basically what that means is what I did earlier. This is just showing you that, see what we remember, the plus, we took the constant terms, pulled them outside, and we split them up and took the Laplace transform of each. I already went over that. Okay. Now this one right here, the Laplace transform of f prime and the Laplace transform of f double prime. So for this one, this is what's going to help you when you start solving differential equations, which in this applied calculus class, that's actually the next section, which would be the next video. All right, so if we have the Laplace transform of f prime, that's just s times the Laplace transform of f minus f of 0, and the Laplace transform of f double prime is s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0. All right, so what they're wanting us to do here is they're saying, given that f of 0 equals 0, f prime of 0 equals 1, express the transform of this in terms of s and the transform of f of t. Okay. All right. So how would we go about this? All right. So we have the Laplace transform of f double prime of t minus 2f prime of t. All right. Now, what does this equal? Well, remember, we can write this as the Laplace transform of f double prime of t minus 2 Laplace transform f prime of t. Okay, so all I did is I took this, I split it up, and I pulled the 2 outside. Okay, now this is equal to, well, what's f double prime? Well, that's this. That's s squared times the Laplace transform of f minus s times f of 0 minus f prime of 0 minus 2 times, now we got the Laplace transform of f prime, which is this up here. That's s times the Laplace transform of f minus f of 0. Okay, so all I did, I just used these. I replaced this with this. See, that's right here. And then minus 2 times the Laplace transform of f prime, which the Laplace transform of f prime is this, which I wrote right there. And so now we need to simplify this sum. And so that's going to be s squared Laplace transform of f minus s times, let's just go ahead and write it out again, f prime of 0 minus, and all we're going to do in this one is distribute the negative 2s Laplace transform of f minus 2 times f of 0. All right, so this is going to be, all right, so what I'm going to do here, this is going to be s squared minus 2s times the Laplace transform of f. So you see how I have the common factor here, Laplace transform f. So all I'm doing is this s squared minus 2s. I'm factoring that out, and I'm left with that. All right. And now we've got, let's see, minus s times, now what's f of 0? F of 0 is 0, so times 0 minus f prime of 0, which is 1. See, that's up here, minus 1. And let's see, minus 2 times f of 0, which is 0. And so this is going to give me s squared minus 2s times Laplace transform of f minus 1, because see, both of those are 0, and that's how they want you to write it. Okay, and so that would be your answer. And that may not make a lot of sense to you now. Well, why am I rewriting it like that? You're going to actually see in the next video when we're solving differential equations using Laplace transforms. Okay. All right. Now I need to bring this table down with me, because we're fixing to do inverse Laplace transforms. And we're going to need the table for this. All right. So to find the inverse Laplace transform, so the inverse Laplace transform of capital F is f of t, little f of t. So we've got 1, 2, 3, 4 examples on finding inverse Laplace transforms. The first two will be pretty easy, and then the next two will be a little more involved. With this inverse Laplace transform, you're going to have a lot of rewriting you're going to have to do. Okay, not in all of them, but some of them you will. All right, so let's look at this. So if we want to find the inverse Laplace transform of this one, so basically what we're doing, here's an easy one. You want the inverse Laplace transform of this right here. So we've got inverse Laplace of s over s squared plus a squared. Okay, that's what we're looking for. Now, what we have to do is we need to come on this side of the table and find out what matches this. Okay, so if you look over here, this, like I said, this is an easy one. There's an exact match right there. It's actually just the formula. You see that? So this is just equal to cosine of AT, and that's your answer. Okay, just a real simple one, nothing to it. I just wanted to do one where I can show you that we're using this side of the table to match it, and our answer's on this side. Okay. All right. Now let's come to some that might be a little more challenging, but not too bad. All right, so this one's equal to 0. So all they're doing here, it's just like this one. Find the Laplace transform of this. And for this one, they're just writing the problem in a little bit different way. So for this one, we got Laplace transform of f is equal to 1 over s squared minus 2s. You just have to solve for it. So what this means is that we can actually write this, or we can write capital F of s is equal to 1 over s squared minus 2s. Okay. All right. Now let's see what we can do here. So we want the inverse Laplace transform of 1 over s squared minus 2s. All right. So we've got to go over to the table and see if we can match this. Now, just glancing down, I don't see anything in the table that has s squared minus 2s or s squared minus as. Okay, s squared minus as, s squared minus 2s. There's nothing in there that has that. But let's do this. Let's take the 1 over s squared minus 2s. Now, all I'm going to do is I'm going to rewrite this thing. Okay? And typically I don't write the inverse Laplace in front of it. I kind of take this right here off to the side and kind of manipulate it, and then I do the inverse Laplace. And matter of fact, what I would probably do here is, okay, I know I'm taking the inverse Laplace transform of this. It doesn't match anything, so I know I'm going to have to rewrite it. So probably what I would do instead is just write it like this, rewrite it, and then do the inverse Laplace. So what I'm seeing here is I can write this as 1 over s times s minus 2, factoring s out. And then if I come over here and look, do you see how I have this? I've got that right there. Okay. Now, it matches almost, right? It almost matches. The problem that I have here is the numerator. That's supposed to be this a in the denominator, which it isn't. So probably what I would do here is I would write this as 1 over s times s plus negative 2. And why did I do that? Because there's a plus sign in between. And since I have a minus 2, I've got to write that plus minus 2. Okay? So now look at this. The denominator looks right. Okay? See, we've got the denominator. But the problem I'm having is with the numerator. I need a negative 2 up there. Well, what can I do there? Well, I need a negative 2, so how about if I multiply by negative 2 to get that negative 2 up there? But if I multiply by negative 2, I have to also come out here and multiply by negative 1/2, because negative 2 times negative 1/2 is 1. So really, I'm just multiplying by 1. All right? So now I'm ready to do the inverse Laplace transform. So I've got the inverse Laplace. Now notice how I have the negative 1/2. I'm going to pull that out of the Laplace transform. And that's going to be negative 2 over s times s plus negative 2. All right, so now everything matches. So this is just negative 1/2, okay? Negative 1/2 times what? Well, that's 1 minus e to the negative at. That's 1 minus e to the negative a. And what's a? A is negative 2 times t. And so this is negative 1/2 times 1 minus e to the 2t. And there's the inverse Laplace transform of that. All right. So you can see it's not too bad. Okay. They're going to get a little more difficult, but you know, they're not that bad. Okay. So let's come down here to this next one here. Let's bring the table down with us. Got to have the table. We like the table. All right, so I need to take the inverse Laplace transform of this thing. All right. So if we look at the table, we can see that nothing matches. Okay, it doesn't match anything, and I would say most of the time that's probably going to be the case. Is what you're not going to find an exact match. Now, I'm not saying you're never going to do it, but a lot of times you're going to have to rewrite these things, and this is one of those times. So I don't have anything where I have a trinomial in the denominator. And this thing doesn't factor. So I'm kind of wondering, I don't know, but let's see if, I don't know, maybe something like these last two. I don't know. Let's see what we've got. Let's see what we can do here. So it doesn't factor. I've got a trinomial. So the first thing that I might try to do is s plus 5 over s squared plus 6s plus 10. That's equal to s plus 5 over s squared plus 6s plus 10. Now let me ask you this. Can you guess what we're fixing to do? That's right. We're going to complete the square on this part. So we take half of the 6, which is 3. 3 squared is 9, so plus 9. And then I have to come over here and subtract 9. So this is going to be s plus 5 over. Now this factors into s plus 3 squared plus 1. Okay? All right. Now, I know what you're probably thinking. You're probably thinking, well, I would have never have thought to have done that. Well, now you will, because you've seen it. Okay? So let's come over here and look. So we can see on this problem that, well, let's see, I need to bring the table where you can see it. I can see it, but you can't. Let me pull this down. There we go. All right. So if you look at this, you see how we have the s plus 5 and the s plus 3 squared plus 1. Let's look at this denominator, s plus 3 squared. Well, if we do that, this a down here, that has to be up here also. And we don't have a s plus 3 up here. See, we got the 3 here. That needs to be s plus 3, and it's not. And then here, this b here, well, that's b is 1. That's 1 squared is 1. We need a, what do we need? We need a 1 in the numerator here. We don't have that either. So probably what we need to do here, I'm gonna see if I can't move this and place it about right in here. Okay, so we can see it. All right. So what in the world do we do here? Well, we need a s plus 3. So what if I write this as s plus 3 plus 2 over s plus 3 squared plus 1? How about that? That looks pretty good. So now, because 3 plus 2 is 5, it's the same thing there. But now I can write this as s plus 3 over s plus 3 squared plus 1 plus 2 over s plus 3 squared plus 1. Okay? So now it looks like to me this one right here, that one looks good. Now it's just this one. I need a 1 instead of a 2. Well, that's no problem. So all we're going to do here, we're going to take the inverse Laplace of each of these over s plus 3 squared plus 1 plus, now I need a 1 instead of a 2. So, well, that's no big deal. I just pull the 2 out, right? We can pull a constant out. S plus 3 squared plus 1. Okay. All right, so look, there it is. What is this? We've got this one right here. So that's e to the negative a. What's a? A is 3. E to the negative 3t times the cosine of bt. Well, what's b? Remember, this is b squared. So this is the same 1 squared. B is 1. So that's 1 times t, which is just t. Okay. And then that's going to be plus 2. And then that's going to be e to the negative at. So that's e to the negative 3t times the sine of bt. B is 1. So that's 1t. And there is your inverse Laplace transform. Okay. So, you know, that one, there was a little more to it than the other ones, but, you know, it is what it is. It's not that bad. All right. So now we've got this one. All right. So let's just pull the table down here and take a quick look. And I'm going to tell you now, nothing matches. Nothing matches that. Okay. There's not even an s cubed in there. Okay. Anything that looks like that denominator. So how do we do this one? Well, these are the fun ones here. You're really gonna enjoy this one. So we're gonna take the 5s squared minus 17s plus 32 over. Now let's go ahead and factor this denominator. That's s times s squared minus 8s plus 16, which is equal to 5s squared minus 17s plus 32 over s times s minus 4 squared. Factor the denominator. And you might already have guessed what we're going to do. So we've got 5s squared minus 17s plus 32 over s times s minus 4 squared is equal to a over s plus b over s minus 4 plus c over s minus 4 squared. Yes, you guessed it. Partial fraction decomposition. There you go. So you should already know how to do this. Okay, so I'm not going to spend a lot of time on it. So we're going to multiply everything by the common denominator. And I might even skip some steps because I just don't want to work it all. And so that's going to give us 5s squared minus 17s plus 32 equals a times s minus 4 squared plus bs times s minus 4 plus c times s. Okay. All right, so we're going to we'll let s equal 0. And when s is equal to 0, you see that? That goes out, and we're left with 32 equals, what is that? 32 equals, what is that, 16a? So a is equal to 2. Make sure I'm going to get all this right. And then, let's see, we can let s equal 4. That's going to knock this term and this term out. And so I plug 4 in for s. And when I plug 4 in for S, I have no idea what I get. I got to put that in my calculator. So that's going to give me 44. That's when I take the 4 and plug it in over here. That's 0, and that's going to equal 4S. I'm sorry, not 4S. 4C. So C is equal to 11. And then, I don't know, you can actually just kind of pick a number for S. We'll do S equal 1. Plug all that in, and you'll have to plug in what A is, and you'll have to plug in what C is, and you will end up getting B is equal to 3. Like I said, I'm not going to show all the work. You should already know how to do that. You had a test on it, so if you had a test on it, that means you know how to do it now. So now, what we have is we have 5s squared minus 17s plus 32 over, and you know it's over this one before we factored it, s cubed minus 8s squared plus 16s, that's a 3, is equal to 2 over s plus 3 over s minus 4 plus 11 over s minus 4 squared. So if I take the Laplace transform of this, that should equal the Laplace transform of this. So I'm sorry, not Laplace transform, but inverse. Did I write inverse on all these up here? Yes, I did. Just making sure. And that's going to be 5s squared minus 17s plus 32 over s cubed minus 8s squared plus 16s is equal to the inverse Laplace. Now I can take the inverse Laplace of each one individually. And what I'm going to go ahead and do initially, I may not have to do it, but more than likely I will. I'm going to go ahead and pull those constants out. And you know, if I didn't need to pull the constant out, then I'll erase it and put it back in the brackets here. But I'm going to go ahead and pull them all out. And we may have to, you know, we may need something, and we may have to multiply by something or all that good stuff. That's 11 over s minus 4. Whoop. No, what are you doing? I'm going to pull the 11 out. All right, so now what we need is our table. Let's go ahead and bring the table over here, and let's just look at the first one. The first one's easy. See the 1 over s, it's just 1. Okay? So that's just going to be 2 times 1. Okay? Nothing to it on that one. All right, let's look at the next one. We've got, I need to put a bracket there. What about this one? 1 over s minus 4. Do I have anything like that? Well, I've got this, don't I? I've got this. So I guess we need to do another step and write this as plus 3 times the inverse Laplace of 1 over. Now remember, all I have, I've got s plus a, but here I've got s minus a. So I've got to turn that into plus. So s plus negative 4. All right. So we'll have to do another step and take the inverse Laplace of that. Now, let's look at this one. Let's see here. 1 over s minus 4 squared. I need to move this. That writing's messing it up. Okay, I see it. Let's get it to where we can all see it pretty good. All right, 1 over s minus 4 squared. So where do I see that one? Well, that's right here, but I need a plus here, so that's going to be plus negative 4. I got to rewrite it into that. So let's do that. All right, so that's going to be, change the color back, plus 11 times the inverse Laplace of 1 over s plus negative 4 squared. All right, so this is going to be 2 plus 3 times, okay, so which one do we have here? Remember, that's this one right here is what it matches. A is negative 4 in this case. So that's going to be 3e to the negative at. And a is negative 4t plus 11. And what is that one going to be? That's, let's see, let me see if I can position this pretty good. So that's going to be this one right here. So in this case, a is negative 4. So it's going to be t e to the negative a. A is negative 4t. All right. So there you have that. And so we've got 2 plus 3e to the 4t plus 11t e to the 4t raised to the 4t. Okay. And this is your answer, and that is the end of the video. So I hope that helped. Like I said, it was a lot of different things, but this is not how you would learn this in a truly just a differential equations class. This is for the applied calculus. At our school, it's the engineering technology program, ICT program. They're the ones that have to take this, and that's what this is for. Okay, we cover this over a 3-day period. We may go into a little more details, go a little bit slower, but it is what it is. So I hope this helped. Check out my other videos. Give me a like, share, subscribe, comment. Thanks for watching, and I'll see y'all in the next one. Later.